Next talk is going to be given by Yishui Zhao. And that talk is entitled Empirically Assessing Opportunities for Prefetching and Caching in Mobile Apps. Yishui, go ahead.
Thank you, Josh, for introduction, and thank you everyone for coming to this session. My name is Yishui, and I'm from University of Southern California. Today, I'll be talking about an empirical study we did that aims to explore the opportunities for prefetching and caching in mobile apps, and now we'll see why we did that. This must be familiar. Mobile apps have become a big part of our daily lives, and some people couldn't even live without them. Well, technologies don't always bring us pleasure, but sometimes anxiety as well. For example, the loading wheel. This is the least thing we want to see in an app, but we're still seeing them every day. This is not that surprising because mobile apps depend on wireless network that has low bandwidth and unstable connectivity compared to wired network. So that makes the network speed the performance bottleneck because we all know that the user-perceived latency cannot be reduced to zero when there's network involved. In this case, if we want to get rid of the loading wheel, we'll have to get rid of the network, and this leads to the very well-adopted technique, which is prefetching and caching. Because the response can be returned from the local cache immediately without any network involved. You might have already seen this woman if you went to my ASE talk 3 months ago. So in that work, we actually took the first step to propose a prefetching technique in mobile apps, and it shows a large benefits. So following up in this work, we want to find more empirical evidence to see how much room there is still for follow-up techniques at a larger scale. So, because there are so few works in mobile apps nowadays compared to the well-studied browser domain, and you might wonder, then why don't you apply those browser techniques to mobile apps already? Because there are so many works there. The reason is the request in browser domain is very rich, which means one initial HTTP request usually need to further fetch some sub-resources, such as JavaScript files, images, and so on. But in mobile apps, the requests are very light, which means one request usually only fetch one single resource, such as JSON data. So the root cause of network latency in browser domain is to load multiple sub-resources, and in the mobile app domain, the root cause is the network round-trip time of one single request. Having said that, in the browser domain, we want to prefetch the sub-resources with one single request, the initial request to get the HTML, because only when we parse the HTML, we'll know what sub-resources can be prefetched. So a technique example would be restructuring the page load process. This cannot be applied to mobile apps where separate requests should be prefetched. So we can conclude that browser technique cannot be applied to mobile apps, and there's still lack of work in mobile app domain. Good news for us. This calls for research attention to prefetching and caching techniques in mobile apps. But hang on, before we propose any fancy techniques, there's actually one key question we need to answer first. And that is, can we even prefetch and cache in mobile apps? Because in our literature review, we found that mobile apps are actually very different from browser domain, so there is still no understanding on the mobile apps yet. With that in mind, we designed 9 research questions that focus on 3 key aspects, and those are the prefetchability of HTTP requests, the cacheability of HTTP responses, and the redundancy of the HTTP requests. To be more specific, in the prefetchability study, we focus on the GET requests because they are read-only and don't have side effects on the server state according to RFC, so they are safe to prefetch. We ask what is the number of GET requests and what's the percentage of them and how prevalent are they across different app categories. because we want to see if prefetching is a good idea in mobile apps or not, and we want to see if certain app categories are more or less suitable for prefetching. Alright, the second aspect is cacheability of HTTP responses. Here, we all know that the prefetchable doesn't mean cacheable because the cache can be stale. Currently, cache staleness problem is still an open challenge, and developers have to rely on the expires headers or the cache control headers to see when the cache will be stale. But the question is, are they trustworthy? So we ask 4 research questions regarding that. How prevalent are those headers, and are they really trustworthy? In the end, the third aspect is the redundancy of the HTTP request. In this aspect, we focus on the redundant requests. The reason is they are the good candidates for caching when the requests are redundant, of course. So the ostensibly redundant requests have the same URL, but they may not be truly redundant if the responses are different. So only the truly redundant requests should be cached and reused. Alright, we asked 2 questions regarding that. How prevalent are the redundant requests, and are they truly redundant? To answer the research questions, this is our workflow. I will tell you how it's built up step by step, briefly, of course, in the interest of time. So we first download around 1,700 top-ranked apps from Google Play across 33 app categories. Among those, around 1,300 apps can be successfully instrumented by Suite, which is a state-of-the-art tool to instrument Android apps. The instrumentation aims to capture the needed information to answer those research questions, such as the HTTP headers. And then we use Monkey Exerciser to generate 3,000 random events and run on Nox Player under Wi-Fi. In the end, we have the logs of the 1,300 apps. But by taking a closer look, we found that there are a lot of apps that have very little number of HTTP requests triggered at runtime. So we manually inspected this and found out there are actually 6 recurring reasons that are shared by those apps, such as obfuscation, and the 6 reasons are listed in our paper. And we also found there are 3 common requests that are always sent by the apps. Those are the loading configuration files, logging with Facebook APIs, or using some monitoring services such as Google Analytics. So in today's apps, we found out this feature. So when you propose some new techniques, you might want to consider this like not the main functional functionalities in the app, but you should consider those requests as well. And we also found the apps with request number between 1 to 3 always only send one or more of those requests. So we excluded those apps to make sure our data is not tainted in the end. So in the end, we have 451 apps in our final set and have requests that is 4 or more than 4. All right. So I won't go into the details of the workflow. Those technical details and the challenges are listed in the paper, such as how to instrument the apps. And I will talk about this later on in my talk because we need to understand this step to understand some results. All right, let's take a look at what we found. Recall our 3 key aspects, and now we'll go through the results one by one. Regarding the prefetchability, remember we focus on the GET requests because they are safe to prefetch. So only the GET request should be prefetched. So this diagram shows the number of GET requests across 33 app categories. So we grouped the apps into 33 categories, and the bottom line means the minimum number of GET requests in all the apps in that certain category. And the top line means the maximum, and the line in the middle means the average. You might wonder, Why there are some bars that doesn't have a top? That's because the maximum is above 150, such as the category 3, which is beauty. So we mark their numbers on the top. Regarding the percentage, the same type of diagram is used again. So we actually use the same type of diagram to answer all the research questions. The get percentage among all the requests triggered at runtime is shown in this diagram. As you can see, the averages are relatively very high, and there are only two categories where the get percentage is below 50%. And so we can see that GET requests are very pervasive, so this is a good news for us because it provides us opportunities for prefetching. We also saw a lot of variations across different app categories, such as beauty and dating. This isn't that surprising if you know how a typical beauty app looks like. If you don't like that. So there are a lot of GET requests to download the images, such as Sephora app. And on the other hand, dating apps has the lowest GET percentage. The reason I think it should be there are a lot of interactions in a dating app, such as the messages or video chat, so they don't usually trigger too many GET requests. And the second aspect, cacheability of the HTTP responses. Remember, we focus on the expires headers and the cache control headers, which are specified in the HTTP responses. So this is the example of the numbers and percentages of expires headers. So our paper has a lot of figures like this, so you can take a closer look there. Now in this talk, I want to focus on the average. This is the average percentage of expire headers and cache control headers. And you can see the distribution is kind of similar, where the cache control header is slightly higher. So we can see that both headers are not always included, but people tend to include slightly more cache control headers. And the next question is, see, we are lucky people include those headers, but are this information trustworthy? So recall our workflow. So I promise you I'll talk about this. Now I am. We send the original request at time t and send the same request at later times. The reason is we want to verify if the future responses can reflect the expired time specified in the original response. Then we can decide whether it's trustworthy or not. We define the 3 untrustworthy scenarios, which you don't need to read, because I'll walk you through with animation and examples. See, this is a timeline of t and t plus x. And say it's September 1st and September 6th. We send a request at different times. And we send a request at, this is the original request sent at t. And we get a response that has expired time specified there. And then we know when the response is supposed to be expire in the expire headers, but we want to see if the later responses actually reflect that. So the first untrustworthy case is we saw some cases where the expired time is way ago. It's even before the original request is sent. This is just simply useless and untrustworthy. The second case is the expired time is before time t plus x specified in the header, but what we saw is the response at time t plus x is actually the same as the original one, so it didn't expire. And the third untrustworthy case is the expired time specified is after time t plus x, but at time t plus x, the response actually didn't expire. So here's the results. We also focus on average in this case. So we can see that on average, cache control headers are around 3 times higher, more trustworthy than the expired headers. And we also saw some apps where all the headers are trustworthy while where the opposite is true. We think the reason should be in some app development, they care more about the caching, prefetching, and the headers. They might have set some standard rules to determine the expired times, while in some other app development, they may just totally ignore this information. So we can conclude that developers should not depend on the headers completely, but there's no reliable alternatives yet. But it's a silver lining for us because there's research opportunities for this type of research. And the third one is the redundancy of the request. Ostensibly redundant requests have the same URL, and on average, there are 20% of them among all the requests. And among the 20% redundant requests, 92% are truly redundant. And there are also some categories where all the redundant requests are truly redundant. So we can see that most redundant requests are truly redundant, so they can simply be cached and reused. But what does this tell us in terms of time savings? Let's take a look at an average app, just a very coarse analysis. On average, the GET request is 28. And in our previous study that I showed before, we measured the average response time is around 800 milliseconds. So in this case, we can save 22 seconds just in one run for if we just prefetching those GET requests. And in terms of caching opportunities, the average app has 28 GET requests, and you can calculate the number of the truly redundant requests is around 6. So in this case, we can save 4 seconds even by only caching the redundant requests. All right, to conclude, we did an empirical study to understand the HTTP characteristics in the mobile apps. We focused on the prefetchability of the requests, the cacheability of the responses, and the redundancy of the requests. We learned that there's a large opportunity for prefetching and caching techniques in mobile apps, but their benefit may vary across different apps or across different app categories. So the app-specific or domain-specific characteristics should be taken into account when proposing follow-up techniques. So we bridge the gap between the browsers and the mobile app domain and provide guidelines for developers such as improving the header quality, and we hope we can encourage more people to work on this exciting area. Last but not least, I would like to thank my co-authors who couldn't be here today with us, but they definitely deserve a shout out for all their hard work. And this work is sponsored by NSF and ONR. Thank you for your attention. I'm happy to take questions.
Let's start on that side of the room, since they somehow managed to raise their hand first.
Thank you, very nice work. So some of the results that you have presented are based on like 3,000 monkey events, right?
Yes.
So I'm wondering, do you see like 3,000 monkey events are enough to like represent the behavior of the application?
Yeah. Thank you for the question. That's a very good one because we made the decision very carefully for the 3,000 events. Because one alternative is to ask a real user, right? But for the nature of this study, we want to see as many requests as possible, and the real user will have bias, or if they're unfamiliar with the app, so we use monkey exercise to generate more. So we tried from 1,000 to 10,000, and we saw the number of requests kind of converge at 3,000. So there's no point to trigger more. It's like more time consuming. So it's more explanations in the paper, but the smallest we tried is 1,000, the largest is 10,000.
Sure. Okay, one more question.
Thank you, Richard. Let's talk. So I'm quite interested in the what you said, the top 3 types of GET request. I'm wondering why there is no advertisement related requests, because most apps may not be using internet intensively, but They
Yeah.
will have some ads.
So for the ads, I think it's a more domain-specific problem because ads, right? They have like this server, and every time they return the ads based on the user's like personal preference, or they have their algorithm. So every time it's just a random, non-deterministic. So we think there's no point to prefetch. It should be a very domain-specific technique done only for ads.
Thank you.
Thank you.
Okay, so thank you, Yishui.